All right, here we go. So, we're going to be finishing up the rest of these examples today. We have quite a few to get through here. Looks like 4 of them, so we're going to get moving. All right, take a look here. So, example 27. Okay, you'll notice here that we've got all these problems have a commonality of a table in them. Okay, so that's like kind of the last kind of style of these problems we're going to be looking at here, dealing with a table and stuff. Okay, so let's go here. So let y of t represent the temperature of a pie that has been removed from a 450 degree Fahrenheit oven and left to cool in a room with a temperature of 72 degrees Fahrenheit, where y is a differentiable function of t. Okay. The table below shows the temperature recorded every 5 minutes. Okay. So letter A asks us to use data from the table to find an approximation for y prime of 18 and explain the meaning of y prime of 18 in terms of the temperature of the pie. Show the computations that lead to your answer. Okay, so we have no graph, we have no function here, and so we're asked to still come up with, though, the value or an approximation for the value of the derivative at 18. Okay, now if you look here in the table, right, okay, we have time minutes, but it's 0 minutes, 5 minutes, 10 minutes, 15 minutes, 20 minutes, 25 minutes, 30 minutes. Okay, that 18 minutes is not on the table. But that's why we're asked to find an approximation here, okay? Because we're not going to get an exact value, but we're going to try and approximate it, okay? Where will 18 show up? Where would 18 show up here on our table? If it were on our table, where would it show up? Right, yeah, between 15 and 20, okay? And so we would expect then y of 18, again, just, if we follow kind of typical behaviors here, we would expect y of 18 probably to be between 292 and 257. We wouldn't, we're not sure, okay? But it is saying that the pie is taken out of an oven and left to cool. So we'd expect that just the temperature is going to gradually decrease for that pie, on down to whatever room temperature is to kind of reach equilibrium, right? And so we expect that these values are just going to continue to decrease, okay? So we expect then that y of 18 is going to be somewhere between here. How, though, are we going to find y prime of 18? Which would be like the slope or the rate of change of the temperature at 18. Any ideas here? Okay. So, the average rate of change, go ahead.
Yeah, I was going to say, would you find like the average rate of change within the table?
Yeah, so we're just going to find the average rate of change between these 2 points. Since 18 is between 15 and 20, okay, the time, we're just going to find the average rate of change between these. Find the slope of the secant line between these 2 points. 15, 292, 20, 257. All right, which is just the formula here. Let's see. I'll do f, or not f, y of 20 minus y of 15. I'm going to write it out very explicitly here. You can just jump to the y values if you want to, over 20 minus 15, or the function values, I guess, if you want to there. Okay, so that's going to yield 257 minus 292 over 5. Okay, right? And so we get, I'll just do this. So negative 35 over 5, which is going to be negative 7. Okay? What would we expect the units to be in this situation with the negative 7? Yeah, degrees Fahrenheit per minute, right? If you just look at what we did in the table here, it gives you what the units are going to be, right? The values of the function y of 20, y of 15, all the y of t's are degrees Fahrenheit. So it'll just be degrees Fahrenheit per, and then what's your x values, or the t values in this case, it's minutes. Okay? What is then the meaning of y prime of 18 in terms of the temperature of the pie? What does that mean? What would that mean in the terms of the temperature of the pie? Well, if y is the temperature of the pie, y prime is going to describe the what? The rate of change of the temperature of the pie. And so at 18 minutes, the rate of change of the temperature of the pie is approximately -7 degrees Fahrenheit per minute. Okay? We could further say that this indicates that what is happening to the temperature of the pie at time t equals 18. The temperature of the pie is what? Decreasing, right? A negative derivative indicates the original function, in this case the temperature of the pie, is decreasing at that instant. Okay? But again, for the context, it makes sense, right? We should have a negative value here. We would, the pie is going to be cooling off. All right, letter B. Use data from the table to find the value of the integral from 10 to 25 of y prime of t dt, okay, and explain the meaning of the integral from 10 to 25 of y prime of t dt in terms of the temperature of the pie, excuse me, indicate units of measure. All right, so now we're going to try and integrate something whose, we don't know the function for y prime, but let's just think about what that's going to be here. Okay. If we integrate y prime, what are we going to end up with? Y of t plus some c, right? But if we're going to do a definite integral, that c value is going to subtract and disappear, and so we're going to end up with y of t and evaluate that from 10 to 25. And so we get y of 25 minus y of 10. Okay? What is y of 25? Yeah, 226. And y of 10, we've got in the table right there. It's 338. Okay, so 226 minus 338, negative 112. And what would our units be here? Just degrees Fahrenheit, exactly right. The quantity here that we subtracted, the two quantities we subtracted are both in degrees Fahrenheit. And so then that's the value. And then, what is the meaning of this? Well, when we integrate a rate, that gives us the net, what? Change. So, from the time t equals 10 to the time t equals 25, okay? So, from t equals 10 minutes to t equals 25 minutes, the net change in the temperature of the pie, we can just say the net change in temperature, is negative 112 degrees Fahrenheit. And that's all we got to say. Okay? All right. Now, oh, go ahead, Keith.
So in a just like similar scenario, what would it be if it was like not prime, if it was just y-t? What would you consider that?
So at that point, if we're trying to integrate the actual function itself, like and given the data in the table is also just the function's value. At this point, right, we're kind of stuck. In a sense, we can still be asked to do something like that, but you would be asked then to use like a left-hand sum, a right-hand sum, or a trapezoidal sum. Because we can use a table and a left-hand sum, right-hand sum, trapezoidal sum to then approximate those values. Okay, so great question, right? So just to make sure you guys heard that, right? If we were integrating from 10 to 25 of just y of t dt, okay, we could use the table of values, I think, to approximate that. Well, now let me think about that. Make sure I got that right. Integrating the table there, and that change from there to there. Those points, yes, because we use the left-hand sum, right-hand sum, and trapezoidal rule to approximate the area under this particular curve, so we would just use those kind of points to help us do that. Yep. So it would be something like that. You would need to use an approximation. Okay? Now, moving on here, though, letter C, a model for the temperature of the pie is given by this function, W of t equals 72, you see what's there, okay? Where t is measured in minutes and W of t is measured in degrees Fahrenheit, okay? So this will give us the temperature of the pie at any time t. And we're then going to use this model to find the value of W prime of 18, indicate units of measure. Now, if you come across a problem like this in the wild on your own, right, and you read these first two questions and you're like, I'm not really sure what to do, okay, and then you come down to letter C and you read that one and you're like, oh my gosh, they give us the function right here. I'm just going to go back and use this function to answer this question and this question. Okay, because isn't this thing asking to, find y prime of 18? Well, I mean, here's the temperature function. I can just use that and get the derivative there. No, you can't do that, right? This is this is for this question only, right? This is asking to use the table, right? And this says use the data from the table. So do not try to use this in these two previous questions. Okay, that won't be right. It's because it's not what they're asking here. Now that we're given this, we can use this, okay, as a model for this situation. So by the way, this won't necessarily match the table here, okay? It's a model, okay? This is actual data recorded, okay, I guess in this scenario, in this context, in this problem. This is a model that we're going to use now to answer some other questions. All right? So letter C, anyway. We want to then find w prime of 18. So at this point, what should we now do? We can take the derivative. With the way these numbers look, I'm going to guess that well, actually, you know what? We could do this without a graphing calculator, I suppose. It's not really necessary. We wouldn't be able to get the exact value. We would get the, well, I mean, we could get the exact value. It's just a little bit, messy with the calculations there. So let's go ahead and just take the derivative by hand. Okay. Let's pretend that this is a non-calculator question right here. Because really, none of these really required a calculator at this point. It's all arithmetic. So w prime of t, okay, what is the derivative of 72? 0. And the derivative of 380 e to the something will be 380 e to that same something, so negative 0.036t, times the negative 0.036, right, the derivative of what's inside there. Don't forget your chain rule. Okay? And so then, bless you, if we want to find w prime of 18, we can just plug the 18 in. Okay, like so. Okay. What would our units of measure be here? Degrees per minute, right? Because again, T is measured in minutes, W is Fahrenheit, so it's degrees Fahrenheit per minute. Okay. And I think that's all we have to, we don't have to describe it. Yeah, so there it is, just right there. Okay. Alternatively, let's say that this is calculator active. Oh, question, Sheldon. Ah, you're right. I did leave that out when I wrote my answer out here. I don't know why I did that. Thank you. Uh, 18 times then the negative 0.036. Okay, there we go. Degrees Fahrenheit per minute. Okay, sorry. All right. So anyway, with that now that solution, right? We have another option. Though. Let's say we did have our calculators available to us, right? We don't need to come up with the derivative by hand here to use our calculators, okay, to do this, right? All we need is to type the original function in. You have two options about how you can do that. Option 1, you can press math 8, right? And we'll take the derivative with respect to x of our function here. So 72 plus 380 e to the negative 0.036 x. Okay, and then we'll evaluate that at x equals 18. Okay, so there's our answer that way, right? I'll just show you that that does match to the 036. Oops, times negative 0.0036. There you go. You see that they do match up there. Okay, so that's one way to do it. For those of you without the pretty type, okay, so without the math print, let me just show you what that looks like. Okay, it's use the nderiv command, nderiv, numeric derivative, okay? We're going to, the first command, the first thing you enter is the function, much like when you do the integral, right? The first thing you put in is the function, comma, the x, just like with integration, you do a comma x. And then for the derivative, we don't have an upper and lower limit, we're just going to put in just the value or evaluating the derivative, so comma 18. So function, comma, with respect to x, comma, at 18. Okay, that's what it would look like, and you get everything there. Alternatively, right, if you don't like that, you can also put the function into y equals, let me clear all this stuff out here, and we can do 72 plus 380 e to the negative 0.036x. Okay, let me go back to pretty type here. Okay, like so. We can graph it. Okay, of course, in the standard viewing window, it's not going to show up because the temperature is, supposed to be kind of high early on, right, in the time there. If you do second trace, right, and you go down to the dy dx command there, whoops, too far, there it is, okay, you can type in the value. So we want to find the value of the derivative at 18. If you do it this way and hit enter, you're going to get an error. The reason why is because your x value needs to be, like your window needs to have the x value that you're trying to evaluate in it. So I'm going to go from x value to 20, and I'll graph it now. Okay, second trace, dy dx, what was it, 18, bless you, negative 7.155, there it is again, okay? Notice that your y values, so the graph doesn't actually have to show up, at least in my calculator. Maybe your calculator does. Okay, I don't know if the older ones need it to show up or not. But for my calculator, I don't need to have the graph actually showing up in my window. I just need to make sure that my x values, the x value I'm trying to evaluate, is within my x interval there. Okay, so as long as your 18 fits between there, then you're good to go. You don't actually have to see the graph. It'll just show it for you. So again, dy dx 18, and then there's that too. Okay. Of course, also now that it's in y1, when you go to do the dy dx on the home screen, you can just use the y1 and evaluate at 18 that way and get your answer there too. Okay. So lots of options. Pick the one that you feel most comfortable with or whatever, and go with that. All right. All right. Moving on. Letter D, use the model in part C to find the time at which the temperature of the pie is 300 degrees Fahrenheit. Okay, so how do we do that? Set the equation equal to 300. Yeah, exactly right. This is like pre-calculus right here. Okay. Again, I would argue here that a calculator is not necessary. Okay, if we want to get a decimal approximation, that will be necessary, right? But at this point, we don't need a calculator because what should we do? How do we solve this? Subtract 72 from both sides, right? Okay, and so let's see, we're going to end up with 228. Okay, 228. Divide both sides by 380. Okay. Once we've isolated that e, natural log, okay, right? Natural log and e are inverse of each other. They cancel each other out, and so we'll end up with, again, I'll just kind of write that here, natural log. So you can say negative 0.036t equals the natural log of 228 over 380. And then final step, we'll just divide over the negative 0.036. Okay. If this were a calculator active problem, okay, you could still just write this. This could be your answer right there. Okay, this is minutes. Okay, so you can still just write that as your answer. If you want to give a decimal approximation, okay, if you want to give a decimal approximation, or if this is like a multiple choice and you want to like match your answer to the decimal approximation answer that they have, on the page there or whatever, I would recommend against doing any sort of decimal approximation until this point right here. And at this point, you would then type this whole mess in your calculator and get the decimal approximation. Okay, so in other words, don't do 228 divided by 380, or don't do the natural log of 228 divided by 380 and round that, and then divide by negative 0.036. Do it all at once. No intermediate rounding. Wait till the very end. Type this whole mess in your calculator and get that decimal approximation. Okay. Okay, and I get about 14.19 190 or 189 if you want to, truncate it around there. Okay? And that'd be in minutes, of course. Okay? Questions on any of that? That wasn't too bad, right? Let's keep going. All right. Let y of t represent the population of the town of Sugar Mill over a 10-year period, where y is a differentiable function of t. The table below shows the population recorded every 2 years. Okay? So here again, in this context, less obvious about whether we expect it to always increase, always decrease, right? Populations go up and down. We want to be a little bit careful here. It looks like, though, the behavior over time is to generally increase. Okay, again, between the numbers, not really sure what's happening, right? Don't know, but at least over the years, in general, it is increasing. All right, so letter A, we're going to go ahead and find an approximation for y prime of 7. So why don't you guys go ahead and give that one a shot? Okay, so take like a minute here, give it a try. Find y prime of 7 and explain the meaning, okay? Explain the meaning in the context of the situation. Show the computations lead to your answer. All right, so go ahead, try letter A. Gabe, if you read letter B, you'll see a question that's like what you were asking earlier.
So what is the difference in what it actually means between what B is finding and what if you're finding the integral of the rate? Like what is like that?
So, the integral of the rate gives you like the net change, okay? Letter B, okay, gives you the average value. So the net change means like the total change that happened between this time period and this time period. How much does the population go up, or well, how much does the population change by between those two time periods? Letter B is asking for the average value. So in other words, like the average population of the town from 0 to 10 years or something like that. Okay? So it's taking like an infinite number of like data points essentially from 0 to 10, right? The population is constantly changing kind of thing. And it's giving you a single average number of the mean of all of those things between 0 and 10. So yeah.
On letter C,
Yep.
is it asking for P prime of 7?
Oh, I see what you're saying. Yeah, I think you want to go with P prime of 7 there. I agree, though. It does look, but I think it is P prime. Yeah, I think it is supposed to be P prime. Because if you look at the P of T, it looks slightly different than the P of 7. Like, it looks like there's maybe something a little added in there, so I think that's supposed to be P prime. Yeah. Okay? All right, so I think most of us have gotten A done. Okay, so there's 515 over 2 people per year, your average. Well, we're using an average rate of change to approximate, right? In the past, isn't that how that's how we started calculus, right? We used the secant slope to approximate, the tangent slope, right? This is asking for the tangent slope at 7, but we can't find that. We don't have that kind of data to do it, so we're just going to use the secant slope to approximate it. That is like a fundamental concept that we use to build all of, derivative, all the derivative stuff that we learned. So anyway, the population of Sugar Mill is changing at a rate of approximately 515 over 2 people per year at t equals 7 years. Let me make a recommendation to you. You don't have to follow it, okay? Be careful about using the words like is increasing at a rate of approximately this per year, or decreasing at a rate of approximately this per year. It can get a little hairy there, okay? If, for example, okay, if we said here at t equals 18 minutes, the rate of change of the temperature of the pie is decreasing at a rate of -7. Well, decreasing and then saying -7, to me, it's kind of like a double negative, and so decreasing at a negative rate would really mean increasing, right? Decreasing at a negative rate would really mean increasing. So that's why it's kind of like, I would say just use the word rate of change, okay? Just identify it as the rate of change of the temperature of the pie. And then you can say this means the temperature is decreasing, that's fine, okay? But be careful about how you say that. Here it's safe to say the population of Sugar Mill is increasing at a rate of approximately 515 over 2 people per year. That's fine, that's not wrong, but just be careful. I would suggest just saying the population of Sugar Mill is changing at a rate of approximately this. Since it's positive, we know it's increasing now. Okay? So anyway, since the derivative's value is positive, the function's increasing. All right, use data from the table to approximate the average population of Sugar Mill over the time interval. Okay, we see that word average. We're asked for the average population, and we're given information about the population. So which average concept are we going to use here? Average rate of change or average value? Okay, so maybe we're not so sure, right? Okay, so it is going to be average value here. It's going to be average value because we've got, so people did say average value, I heard it, but we weren't quite so certain about it, right? So we are given information about the population. We want to find the average population. If we were asked to find the average rate of change of the population, then we would use average rate of change formula. But since we're given population information, we want to find the average population, average value. How do you find the average value? Well, it's the 1 over, in this case, 10 minus 0, because that's our A and our B. Integral from 0 to 10, and we integrate the thing whose average value we're trying to find. So in this case, like y of t dt. Okay, so that's the setup. Show the computations that lead to your answer. There's our setup. Okay, but of course, for our purposes, right, we can't integrate y of t. We don't know what it is, nor do we know the integral of y at 0 or the integral of y at 10. We're going to approximate it using a left Riemann sum with 5 equal subintervals. Okay, 5 equal subintervals. Okay. Why don't we just start with that? Right. So why did I write this out instead? Okay. So I wrote it out because sometimes the importance, it's like you get a point for showing up like your initial setup kind of thing. So that's why I wanted to put that there. Okay? I'll also say I think it's important too because I find that students forget this 1 over 10 minus 0, right? We can get so bogged down in doing the left Riemann sum part and forget the 1 over 10 minus 0 that you have to then also multiply by, right? So you might like get this left Riemann sum, no problem, but then you have to multiply further by 1/10. So that's another reason why I did it too. Okay, so squiggly equals, because we're approximating here. So 1/10 then times. Okay, so 5 equal subintervals. Well, let's just see how many subintervals we have here. 1, 2, 3, 4, 5. Okay, there it is. That's nice. Okay. All right. That's the only one we could do here. Okay, that's pretty much that's our only option. I mean, I guess we could do like 3 subintervals, but they wouldn't be able to be equal lengths, right? We'd have to have different lengths and stuff like that. But anyway, all right. The widths of all these subintervals are going to be what? 2. So if you want to save yourself a little bit of a headache, you can just put a 2 and then another parentheses here. Okay, and we're just going to do all the left endpoints. So for our first interval here, what's the left endpoint's height? Yeah, 2,500 there. And they're going to add to that, okay, for the next interval, what's that height? From 2 to 4, what's the left endpoint's height? Yep, 2,912. And then so on and so forth, right? It'll be 3,360. And then for the next to last interval, it'll be 3,815. And then finally 4,330. Okay? Each one of these heights will get multiplied by the width of 2, right? All these widths are 2. Okay? And so then we can leave it like this. Actually, if we want to, we can just leave it and say that's our answer. Okay? Yes.
Did you how do you know when to put the 1 over 10 there?
What are we asked to find here?
Well, it's just because it's how you find average value.
Exactly. It's just because that's how you find average value. It's the 1/10, the 1 over b minus a times the integral. So this right here is being approximated by this right here. The integral, whose value we cannot find exactly, we're going to approximate it using this the left-Riemann sum, and then the 1/10, that's from the 1 over b minus a. The average value. Okay, so we can leave it like that. We actually don't need to compute the rest. We can just stop there and say that's our answer. Okay, we can stop there and say that's our answer. Okay, so there it is, average value. So, and this would be in what unit? Oh, sorry, go ahead.
So can you just go over again how you would find the average rate of change?
Sure.
Yeah.
So if we wanted to find the average rate of change of the population here, that would be the, you would need an interval again. So let's say we want to find the average rate of change of the population from 0 to 10. Different question, right? Average rate of change of something is that something at the one endpoint minus that something at the other endpoint over b minus a. It's exactly what we did right here. This is the average rate of change from 6 to 8, for example. So that kind of thing. Okay? What would the units be here for this answer, though? It would be in people. It would be in people, yeah. Okay? It's the average population, so it's number of people. Okay? So it's the average population of the people from the interval from year 0 to year 10. Okay? All right. Letter C, model for population of another town, Pine Grove, of the same 10-year period is given by the function there, where t is measured in years and p of t is measured in people. Use the model to find the value of p prime of t. Okay? Again, it looks like here this function probably is not a calculator active function, or this is probably not calculator active here. Okay? We can use our calculators and stuff, of course. But let's go ahead and do it without a calculator. So we'll find p prime of t. Okay? By the chain rule here, that 2 is going to come out front. And the new power will be 1 times what? Derivative of what's inside, which is just a 2. Okay? And we're going to find p prime of 7. So p prime of 7. I'm going to go ahead and do the 2 times the 2 there. And then 2 times 7 plus 50 to the 1, like that. Okay? Again, you can stop there if you want to. What will the units be for this quantity? People per year. It's the rate of change of the population, so people per year. Okay? Of course, we can also, type this. Excuse me. So 256 is the actual value there, and of course we could use our calculators. Math 8. With respect to x, we're going to do 2x plus 50 to the 2 evaluated at 7, and there's that 256 there as well. Okay, using your calculator and the derivative command. Okay. All right. Letter D. Use the model given in part C to find the value of the integral from 0 to 10, or so 1/10 of the integral from 0 to 10 of p of t dt. Explain the meaning of this integral expression in terms of the population of Pine Grove. Okay, so what do we recognize this integral as? An average value of the population from year 0 to year 10. Okay, exactly right. So we're just going to evaluate this now using our function there. So the again, let's assume this is non-calculator, and then we'll proceed with our calculators at the end to check ourselves. Okay, definite integrals. It's been a while since we've had to do these by hand, right? Some of you guys have already started the quiz review, and you go back and look at those definite integrals, you're like, oh my gosh, how do I even do this? Kind of thing. So we have to refresh our memory a little bit. First question, can we integrate this as it's currently written? No, okay. So of course Mr. Wood wouldn't ask that question unless that was the answer was no, I guess, right? So anyway, Kind of begs the answer there. Anyway, so we'll square this out, okay? 2t plus 50 squared, it's 2t plus 50 times 2t plus 50, so we're going to get 4t squared, right? Plus 200t plus 2,500 dt, right? You do 2t plus 50 times 2t plus 50, and that's what you're going to get there. Then we integrate. Okay, so integrating 4t squared is going to give us 4t cubed over 3, plus 200t will be 200t squared over 2, plus 2,500t evaluated from 0 to 10. And don't forget that 1/10. Where am I going to put that? I guess put it in front here. Like that. Okay. We're not ready to be done yet. The very last step here we need to do is actually plug in. I'm going to simplify the 200 and the 1 there. And so we can say 1/10 times 4/3 times 10 to the third plus 100 times 10 squared plus 2,500 times 10, like that. Okay? You could also, of course, let's see here, maybe I should be a little more careful. We could, put in the 0 as well. In this case, right, it's not necessary if we, again, I would suggest every time you have a 0 as a limit of integration, convince yourself that it is going to, that the lower limit will be 0 when you plug 0 in. Let's convince ourselves 0 here is 0, plus another 0, 2,500 times 0 is 0. So 0 plus 0 plus 0, 0. So yes, it'll all cancel out. If you want to, write it in here, you can. 100 times 0 squared plus 2,500 times 0. And the only other thing here, I got to make sure that 1/10 gets multiplied by the whole quantity. So I actually have to put like one more set of parentheses in there. Okay. If I didn't put that extra set of square brackets in there, the 1/10 would only multiply with my upper limit, which again, mathematically, that would be okay in this situation because the lower limit doesn't need to be multiplied by 1/10. It's just going to be 0. But, it's still good math, good practice to do that. Okay, questions on that? We're not done yet, though, right? We have to explain the meaning of this. So again, we already did that, though. We did that first, right? Okay, so, and I don't know here. How do I want to describe this thing? So what you can do is say that this is maybe equal to, like, I don't know, a variable. Let's just say it's equal to x, okay? You can say then the quantity x is the average value of the population of Pine Grove from year 0 to year 10. Okay. Or from time t equals 0, maybe it would be better. From t equals 0 to t equals 10. I like that better. Okay? T equals 0 to t equals 10. Alrighty? Questions on any of that? Keep it moving, Mr. Wig. You got it. All right. 29. All right. Very similar thing here. Rate at which water is being pumped into the tank is given by the continuous increasing function, R of t. Continuous increasing function. That's a new piece of information. All right, we haven't been told it was automatically going to be increasing, right? The pi one, we assumed it was decreasing, but here we're told for sure it's increasing for the entire time. That's helpful. A table of selected values of R of t for the time interval 0 less than or equal to t less than or equal to 20 minutes is shown below. Okay, so this is a rate. Okay, a little bit different though, right? Before we were given, actual people, not the rate of change of people. Here we were given actual degrees Fahrenheit, not the rate of change of the temperature. But now for our next one here, we are given the rates at specific times. Okay, so let's have you guys go ahead and answer letter A. I'm going to read A for you here real quick. It says use a right Riemann sum with 4 subintervals. What word, what other adjective is descripting here that is missing that we sometimes see? Equal, okay? If you look at your table, we're not going to have equal subintervals here. that's okay. So go ahead and try this one, please. All right, go ahead and try letter A there. Give that a shot. Okay. And make sure you answer, is your approximation greater or less than the true value? And make sure you give a reason for your answer, right? We've talked about how we know when right Riemann sums, left Riemann sums, trapezoidal sums, midpoint sums, when those are over and under approximations. So go ahead and answer that. Notice you're not asked to interpret what the meaning of your answer is. Just give whether it's an approximation, whether it's greater or less than the actual value would be.
What did you do calculator active or not?
That's a good question.
When you get down to B,
When you get down to B, average rate, and that is the rate. I mean, again, if you want to get an exact value, then yes, you would need your calculator to do that. If you want to just get an arithmetically equivalent, kind of thing, you wouldn't need a calculator for that, I would think.
I did both ways.
I think for letter C, though, you would need a calculator, so I think this would be
So
calculator
overall,
active.
we calculate active.
Probably, yeah, probably. So yeah, feel free, guys, move on to B and C there. Give those a try, too. Okay, see what you come up with. How about we just do that? Okay, so go ahead and work through B and C as well. Okay, and I'll kind of come around and help, too, once I get through here.
Yeah, it would have to be calculator active anyways. Probably R. You made all that extra R.
Bless you.
It's basically how I feel about everything.
Oh, I'm sorry. Yes, with letter B, you would. I apologize. Yes, letter B, you would need a...
You would need a calculator.
Yes. Because of what you're being asked to do there.
It doesn't matter, we can do it by hand.
Yes. Sorry, now that I've read it more thoroughly there.
Is there a reason why you can't do it by hand?
Well, so which of the two average formulas would you be using? Would you want to use the average value here, or would you want to use average rate of change?
Average value.
Right. So we don't know how to integrate e to the 0.03t.
Okay, so I didn't do it wrong.
Yeah. We can't integrate e to the 0.03t.
Did you get something like that?
Kind. I mean, you could probably figure that one out. Not too tricky, but we will be able to eventually integrate this by hand. But right now, we don't have the skill. We haven't touched the skills yet.
It's going to be a while before we have that, though, right?
No, actually, that's like the next thing after this quiz. We're gonna learn how to do. So,
Let's put off some of these things.
right. Requires something called a U-Substitution. Change of variables.
This would be you know what I love the most? Going into AP Physics every single test and just hoping that I fail just right. Every single time. I'm always hoping like, if I fail just right, I'll still get an A. That's how, yeah, if you get a 60, it's like a 50 through a 60 or something.
Oh, I hate you.
No, 60 and above.
60 and above.
60 and above, you get a 95.
You need a 65 or a B.
Yep, I remember. I remember in Canada.
Yeah.
I was awful. 47% is a C, 47% is a C, and that was like my mantra for the whole college.
I aim for 70. That'll put me in like an 88 range and I call that good.
I am for a 50%.
If I get 70, I call that success. No problem.
Chances are if you know 3 of the answers, you're doing alright.
I usually not do not guesses, but I can argue like
Exactly.
Alright, so take the tank of the gallon of water. Zero, you just model given it perfectly. Fine, how much water? Okay, so
Oh, wow.
But I also love it.
So, yeah, and the only thing I'm gonna warn you about, I know because there's a lot of space.
Oh, yeah,
Just make sure we're. Yes. We'll give you more space.
I got this. 100 plus F9, 0 to 20.
Well, that one you have to.
Yes.
And 103.
Yes.
20.
Favoritism.
What's alpha X?
Yes. Or wait. No, all you're asking is just to
You're
find.
finding how much is finding a amount.
Are we asking
Really?
for an average value?
Really?
I think your
It
answer's
just says approximate this.
You're adding all the gallons
Oh.
because that's how much it increases over time. So you can do 34.255. 34.255 times.
The average rate change is average value. You're not
Okay.
Alright.
Hold on. So what did you do? I just put it in X. Okay. Alright. So it's not like I actually did anything wrong.
That is right. What you have set up there. No, it
Why
is.
wouldn't you, since you have the rate?
Okay, because when you want, so for example, in the last problem here, I told you this was an average rate of change, right? We're not supposed to. Here we were given the people.
Are we doing?
We want to find the average rate of change.
Keep talking
So we did people minus people. Times 7, we did this. Okay. When you want to find the average value of the population, we use this method.
And I'm all for it.
Right? Why is that though? So here, you were given the actual people, the actual people, you want to find the average value of the population.
No, not really.
You want to find the average change, use that.
Yeah,
That seems so fancy.
I know.
Coaches
We fit in 1/3 last Friday.
It's so weird having to use those.
That's fine. I know all these
In
what class?
All right. Shh. Here we go.
And then it's
Later, we got the
Okay, here we go. Okay, we got one more there. All right. Letter A is an over approximation. Right? Write Riemann sum for an increasing function. Write Riemann sum for an increasing function over approximation. Okay, and there's, of course, your value there. Okay. We have to be careful, right? Make sure you're careful with these intervals, right? The first interval has a width of 4. The next one has a width of 5, and then 8, and then 3, okay? But you're always using that right endpoint. So 4 times 28, 5 times 33, 8 times 42, 3 times the 46 there. Okay, like that. Yes? Because we are not asked to find the average. In this case, we're just approximating this integral, which all we want to do then is just that. If we were asked to find the average value of the interval from 0 to 20, or the quantity here from 0 to 20, then we would do that. Okay? So yeah, no 1/20th. The 1/20th was there in the previous problem, or the 1/10th was there because we were using the data from the table to approximate the average population. You see the difference here? We were asked to approximate the average population, so we had to put the 1/10th in front there like that. Here it's just approximate this integral. So, letter B, there's your setup, okay? But Mr. Wid, the question asks for the average rate. Why did you use average value here? Because we were given rates. And if we want to find the average of those rates, we're going to use average value. We're given rates first, so given rates, okay, find average rates, average value. Okay, if you're given rates and you want to find the average rate, that is the average value formula you want to use there. Okay, Gabe?
This is for C.
Okay. And so then there's letter C.
Do you not use prime because it is already the
Exactly, it is already the rate. So when you integrate a rate, you're getting the net change in quantity. So again, the integral alone is not our answer. The integral alone is not the answer. You want to add to that the 100 there. Okay, Stephen, I never asked you your question. Did you get it answered?
Oh, I was just going to ask about the antiderivative because I was confused on the same.
Okay, but do you see now? You're okay? Okay. All right, last one here. Last one. Okay, a bowl of soup is placed on the kitchen counter to cool. Let T of x represent the temperature of the soup at time x, where T is the differentiable function of x. What's a definite integral? That is an integral which has got limits of integration as opposed to an indefinite which has no limits of integration to it. Right? Okay, indefinite because it's not kind of defined over a particular interval. Definite because it's...
I've definitely been paying attention. It's just...
Yes. Or indefinitely paying attention.
Now you're making my head.
I don't know either. All right, so anyway, example 30. Go ahead, guys, work through that one, okay? We'll take some time here in about 5 or 10 minutes or so to go over it. If you finish this example, please feel free to go on to the practice quiz, okay, and work on that. But I'm going to, we'll go over this, so go ahead, try this one. I don't think there's anything crazy in here.
Yeah, it's definitely T prime. Yeah, it's T prime.
Yes, A is a T prime. All the other T's are T of X's. Okay, so go ahead and give that a try. And again, if you've already finished 30 and you're waiting for Mr. Wade because he's too slow for you, okay, feel free to move on to the quiz review, all right, and work on that. If you already finished the quiz review, feel free to work on problem set 4. If you already finished that, great. Okay, so yeah, Sean. Yes. Gabe?
So is an indefinite integral the thing where we integrated it and we had to add the plus c?
Correct.
Okay.
Right.
And then did you call the definite integral when we had to find c?
The definite integral is when we have an integral with limits of integration, because it's like defined. It's got a, it's a essentially like, I guess it's, I don't want to say it's finite, but it's defined over a particular interval. Indefinite, there's no interval there, so that's why we have that plus c and stuff like that.
Did you find it or did you not?
Okay, an indefinite integral will always result in a function. When you indefinitely integrate, you result in a function. A definite integral will result in a value, a quantity.
You're going to integrate, making it T of x, so then it's going to be 12 minus T of 0, which is 95 minus 108, which is negative 13.
I guess you're right. It's whatever. It's whatever. What's different?
Okay.
No bad.
So Mr. Whitmer, they don't give you like specific, like they don't give you minutes or seconds.
Ooh,
So you know.
oh, look in the table. Look in the table.
Oh, okay.
I was just thinking the same thing, but then yeah.
Say theoretically they didn't, what would you do?
That's a great question. I don't know. I'd say 0 units of time, maybe, or something.
Okay,
Yeah,
but you
just
would
go from
definitely
there.
write something.
Well, if they don't give you units, I think then you're safe. You should be good, kind of thing. Yeah.
What is like 1, 2, 3, 4?
Right. So which one of those formulas do you use now for letter B? Okay. Integrating the derivative. When you integrate a derivative, what you end up with? The original function. So integrate t prime results in just t. You will then want to evaluate t at 0 and 12, right? It's subtractive,
It's
right?
4, it's base.
Use that 4.
Times the 2.
You mean like this?
I understand how like.
Nope,
the
I like that.
function equals that.
Yeah, I do like smell a lot of crack.
Right? That's what we just kind of said.
Yeah, I get that.
So we want to evaluate though, it's not indefinite. We want to evaluate from like 0 to 10, I think, right? 0 to 12. Okay, memory. Okay, so once we've integrated something, how do we then go about doing this part of it? Yeah, we just plug it in, right?
Simple math is not my thing.
So like, did you use the second?
Is it sad that
This is more, I'd say this is actually like the first fundamental theorem, because second fundamental theorem is when you take the derivative of an integral. So we're not taking the derivative of this thing, we're just evaluating this. When you integrate something's derivative, you get that original thing.
2x cubed?
And then how do we evaluate a definite integral? What do? We do upper limit minus lower limit in that,
How do we know that we have to like integrate?
because it was asked for us to do in letter A. It's just what a letter asks us to do, integrate t prime. That's all it is.
This math gets really, really repetitive.
Yes.
Wait, so you got 2 8 to the 7?
My actual score has it.
I have the ACT on Saturday.
ACT's a lot easier than SAT.
Average value of the temperature of the soup.
Does it take the same amount of time as the SAT?
It's a little longer.
What do you mean it's a little longer?
It's, yeah,
That's irritating.
but it's also, you're a lot tighter on time, so it doesn't feel as long as you're running.
That's good. So this would just be.
So C would be the average
temperature, not the average rate of change in temperature, right? Because it's just heat.
Correct. The average value of the temperature. Or the average temperature would be fine to say that too.
On the interval of 1 to 12 minutes.
Yes.
Look, the average temperature is over the time interval 0.
Yes. Yes, go ahead. Questions? Again, if you got this one done, feel free to move on to the quiz. We'll go over this in just a few minutes. Good. Alright, I already have the whole quantity. Yeah, so anything that always results in a net change. That is maintained slightly. We talk about like integrating like velocity with gradient position. That's the net change position. We also call that like the net displacement. So if you're going like net change will be temperature. So in other words, you know, do this. I mean, it's like the regular basis or like. The math is what it is, you know, it's not like calculations where it's like, Aaron's not coming to so that's what correct. This is a rate of change. This is like the total change. In fact, I think there's one you're able to is there a limit? All done. Yes, two first names. What am I supposed to do about it? Wait, what? Okay, folks. Okay, hopefully I did those all right.
Most likely not.
Most likely not, no. Given my track record recently. Okay, questions on A or B?
Yeah, I tend to get it right.
Okay, we're all good there? Keep in mind, folks, right, anytime you integrate a rate, you will you'll end up with a net change, right? A net change over that particular interval that you're integrating. And then there's letter C. Okay, again, I didn't bother coming up with the actual approximation. 1/12, and then times these 3 trapezoids there. So, we just did what? 4 of these table problems? We just did 4 of them. Just did 4. Okay? So. 39? Okay. So no additional homework tonight, just work on that quiz review. I hope you find your wallet. Have you checked the front office? I did. Yeah.
Where'd you lose it at? A class? Or, I don't know, like,
I'll be right there. You want to ask right now, you're saying? Yeah, let me just stop the video here. And then.
I'm gonna start.